What is the room number we're getting in?
You're doing the experiment now, right?
Yes, I'm just going to write out the number in case some people have, you know. What was that sound?
Really?
Oops.
Small cat laughing.
That's Yedam.
Yeah, that was the
That's
Adam.
Yedam. That's actually Yedam.
Is Yedam laughing? Is that you?
She joined and she didn't know the mic was unmuted and she laughed.
There you go.
Yeah.
The horror, the horror. Oh, the video's up. Let's see if I can get this so that it can be seen. Okay. We're in the elementary library because I'm hoping, at least according to the experiments we've done the other day, I can't be seen if I do that. So I'll need to go down there. That's a pain in the neck. Well, I'll just hunch most of the time. Okay. So we're going to be doing the experiment today on whether you can fill an object from the outside. If I move the charge from the outside over here, will it be different than if I move the charge from the outside inside? Now I'm going to put this on an insulating surface so that you can see that it's so that it won't leak charge that way. The other thing I have is I have this. This will actually give me a somewhat of a measurement of the charge. So let's just have a look at what a Van de Graaff generator does. Ooh, don't drop out of the pipe. There we go. All right. Plug in the generator. Whoa, the dry air really does make a difference. That field is so much stronger than in the science lab the other day. How far away am I going to get this zap? Whoa, that's significant. Okay. So, in theory, I should be able to take the charge and put it to the outside here. I've done it twice. 3, 4, 5. Now, in theory, that's it. You should be able to see. Oh my goodness, that's going absolutely haywire. Let's discharge that and move it close to here. Not so much. If I touch it, there's a bit of change. Not a huge amount. There's not a huge amount of change of charge. Let's see if we can see how far. Actually, I've already discharged it out. Not much. 1, 2, 3, 4, 5. Yeah, there's static charge there, but it's not. It doesn't actually jump. The charge didn't jump to me. Let's try it from the inside. Every time this sparks across, you're equalizing the charge between the loop and the Van de Graaff generator. That's 5. Every time I go in, there's a snap. Well, the snap only happened the first time from the outside. Every single time there's a snap going in. I can feel that. That is making the hairs on the back of my arm stand on end. Let's see what happens. Actually, I'll discharge this first. What?
Uh-oh.
Yeah, indeed. Why did that not work? And then it snaps me when I touch it with my hand. Maybe it just needs to earth. If I touched it with this, it didn't earth. That's why.
Maybe it's not giving it enough.
Stop it! Stop! Ow!
Oh.
Can we call it instant karma?
Instant.
Mr. Hendro, stop swearing.
It only counts if I swear in English, doesn't it?
It does.
Bruh.
Swearing
In
in
that
any
case, can I swear in Spanish?
No.
Ching chong long pong ping pong.
That's not Spanish!
His name
Oh
is
my
swear.
goodness.
Si, senor.
That's you, Mr. Hendro.
That's amazing. I can feel
Or
that.
Hendro, or Hendro.
Maybe it's not.
Let's not talk about it, okay? I caught myself halfway
Hey,
through.
now
Okay?
I'm not. Now I'm insulated. Why is that taking so long?
Miss Hendro, touch that ball thingy.
I want to see what it does, no? We're so curious.
It hurt.
Mr. Hendro, the ball is shiny like your head.
Except it might have a little bit more hair than you.
Actually, that's not a huge amount of difference. Why is there not a huge amount of difference? I go to the outside.
Is it like flat in the bottom of the bowl thing? Or is it like rounded up?
You know, I'm going to just go directly and try to move, because that's already got charge on it. If I move this over here, can I do that? Let me get that close enough. Can I get that to zap between the two? That's too high.
Careful.
Okay. That's continually generating charge. Yeah. You can see that zapping on the outside.
Why are you putting your hand in?
To see if I can still feel a field. Why can I still feel
Me
a
at
field?
3 a.m. be like,
What's going on here?
Maybe it's not like flat. Maybe it's
Miss
like
Hendro, just lick
Oh,
it.
that's
It'll
weird.
help.
Okay, that's super weird. I can't feel anything on my hand, but all the hair on my arm is standing on end. That feels super weird.
oh, I was confused for a sec because I thought you were talking about the hair on your head, and I was like, what?
I wonder if you can see that. Oh, I know how to do that. I know how to do this.
Wait, I'm confused about what's happening right now. I don't
Now be
understand.
quiet.
So, basically he's trying to transfer the energy.
No, I get that, but I don't understand what just happened. Like, he was putting the charge or
Well,
something.
neither does Mr. Hendra. That's why he's like, oh
I
my
don't know
god.
why the outside thing and the inside thing didn't work. I'm trying to figure out a way to show that there's a difference outside and inside.
So the experiment failed?
No, something else has failed. I don't know what it is.
Miss Hendro.
I've seen someone do this correctly. Oh goodness, that's not good. Now I'll fix it later.
Mr. Hendro, maybe it's because you're touching it to the bottom, so what you need to do is touch it to the side?
I heard if you lick that big ball, you'll get magical powers.
Okay. Let's see if this works better. So, can you see the little... That's going haywire. Let's get rid of that. So you see the electrophorus has no charge on it at the moment?
Mm-hmm.
I think that's an electroscope. There you go. Can you see the charge going up there as it gets closer?
Mm-hmm.
Can you see that little wiggly thing? That tells you that there's a very high voltage nearby. Okay, if I move it back away again, it should go down, but it's already been charged. There's been some sort of leakage. Okay. Now, if I do this and I charge the outside of this sphere, in theory, if I move this towards it, you should get the same. Yep, there is a charge there. Can you see the charge on the outside? Now let's move it on the inside, see what happens. Get it in far enough. There is no movement. Can you see that?
Yes.
Yeah.
Yes.
All right.
Yes.
There's no movement there, but if I go to the outside, there is the field.
So in theory, the thing should work, but it didn't.
Can you see the field moving there?
Yes. Mr. Hendro, what is that tool called again?
It's not an electrophorus. I think it's called an electroscope.
Electroscope. Mr. Hendro, try putting the rice cooker bowl around the Van de Graaff.
Pentagram.
Sorry, say again.
So try putting the rice cooker bowl around Van de Graaff. So like the Van de Graaff is touching the inside.
You want to put the Van de Graaff ball inside.
Like
Yeah.
a hat, you know?
How am I going to hold it while I do this?
With your hands.
With
No,
my
no,
hands.
No, you
With
just
my hands.
touch it.
Okay,
Mr. Hendro,
drop it,
just
just
don't
drop
be
it.
just don't be a baby, you know? Just get a little bit of water, on your
I will
hands
only
and do it.
cry like a baby if I have to.
We'll send Mr. Hendro. You got
Oh,
this.
goodness, that's a spark. Which means that the bolt, but it stopped.
That's called electricity.
Yes, but there's
Well,
a
you
gap between them. 3, 4, 5, 6. Oh, that's the ray. Let's see what happens if we do it over. Don't hurt me.
Mr. Hendro, it's probably just still sparking the sides though.
Can you feel it?
No, I can't.
That's awesome.
Because I'm grounding this, so there's a flow of some sort.
Tape it from the ceiling, Mr. Hendro.
The thing
Dangle it
is-
from the ceiling.
The thing is, the principle of a Van de Graaff generator, is one where this piece is actually a hollow sphere. So when you're building up the static charge here, what the static charge that goes in here should always be able to generate onto the outside. That's why it's called a static electricity generator. In the same way, I should be able to do the same thing if I put this over the top. So if I take this away and swap it with this, it should also function like a Van de Graaff generator. Can I jerry rig this with maybe hooks? Let's jerry rig this with some books in here. Let's get over the top. Yep, beautiful. Over the top there. Yep, still beautiful. And you'll be up there. Not quite. Needs one more book to make it up to the right height. Or I'm in a library. I can just borrow a stack of books. Okay. George Washington Carver, you can hold up a Van de Graaff generator, even though that's not your preferred field. Okay. That's not nice. That's not nice. That's getting stuck. That's not good. That's not good. Biographies everywhere.
What are you doing?
Please work. That pops out through the top. There we go. Have that there.
Hey!
So I can just sit that like that. Please work.
It looks so weird.
This
Dylan
is
kind of
definitely
like
not
you.
gonna work.
I can feel the big. Yeah, it's not quite correct. It's zapping much closer. That also may have to do with the shape.
I think the hole is too big.
There's a lot of static charge there. Maybe if I go from the top. Yeah, it's zapping, but not much. I think it's because you also have the surface of this also becomes statically charged. No, let's try one more thing. Let's try one more thing.
Wait, Miss Hendro, is it still Okay, never mind.
What potentially we could try is because what happens with the Van der Graaf generator is actually just sits on top of that. So let's just try and balance that then without touching. My battery is running low. Why is my
Oh, Miss Hendro, it's falling.
Thank you, Kyle.
Wow.
Whoa, that's a big difference.
That was good.
I predicted it, Mr. Hendro.
I love you too. How do I get that to balance? I don't want to
Tape it.
Gravity.
It is touching the pole thing.
That's not balance.
Yeah, it might be good. It might be as good as we get.
I can do better.
Oh, that's better. Yes, but now it's zapping between that and that surface there.
This looks so ghetto.
I mean, okay.
Okay, that's having a decent jump. Now I wonder what would happen. I wonder what would happen if I took away this surface that generates. Oh, don't do that to me. So, oh wow. Why is it not counteracting the zaps? Not counteracting the zaps.
Mr. Hendro, it's falling.
So this is also this is also building up static electricity, but I don't have anywhere near the amount of. I don't have anything happening here. So this is generating static electricity, but it's just leaking away.
Because it's cylinder.
So nothing's happening. If I'm filling this, if I fill this from the outside, nothing happens. Is that really jumping up? Try that again. Whoa. Huh. So the static electricity must be jumping from there to the electroscope. That's interesting. So it's charged, but there's not, why does it take so long to actually end up doing the jump? 2, 3. Huh. You have to be fairly close to make it happen. Let's try to see it from this direction, see if you can see when it will happen. I'll just discharge it there. I will discharge it, silly machine. Why are you charged there?
Maybe one of the electron jump farther.
Huh. Take a few seconds before it jumps. 2, 3. Why is it not doing anything there? Oh, it could be these metal bits at the side, maybe. No. In that direction, it actually has to almost touch for it to move. But from this direction, it's already getting the magnetic field there. Maybe it's this flat surface over here. That's amazing. Interesting. Okay. So this experiment did not work very well. However, if you try to charge this from the outside, it doesn't get a huge amount of static electrical charge. Okay, there's not a huge amount there. I'll even try and I'll even put it on an insulator and see what happens. So if I move the insulator close, come on, don't drop. If I move the insulator, if I move the bell close, it's not really building up a static charge on the outside.
It's falling.
There is a zap, but it's very, very minor. There's a limit to how much voltage I can put onto the outside. So it's zapping, but it's zapping really, really close. Like I would say that, oh no, it hasn't done anything great. So it's about a millimeter or two away. But if I change it to the out, I don't want to do this. If I do it on the outside, the zap should be a lot greater. Yeah, it's zapping from there. Yep. So it didn't quite work as well as I'd hoped. That didn't work as well as I hoped.
No more lab.
Pardon?
Nothing.
Does it prove a point? What can I change?
No, it doesn't prove a point.
Maybe you should get more safety stuff.
I have an idea, Mr.
It's falling.
Hendro.
Yes.
All right, so next time you do this, you put the Van der Graaf like that. You don't turn it on. You use an insulated tape. You tape the bowl over make sure it's over, not touching, but over the Van der Graaf generator, right? You turn the Van der Graaf generator on, correct? So then it shocks the sides of it. So that's what it's like putting the charge in the inside. Then next time, you just hold it next. You know what I'm saying? Does that make sense?
Not really. So you're saying use an insulating tape between the two electrical surfaces?
No, just hang it from the ceiling. The rice cooker from the ceiling.
I'm actually wondering. I'm wondering if the layer inside there. Can you see that Teflon layer inside?
Yeah.
Yeah.
I'm wondering if that Teflon layer isn't causing a problem. Because the
Just
other
use
time
like
I
a
saw
normal
someone do
metal
this,
pot.
they did it with a paint tin.
Also, yeah, why don't you just use like a rounded metal bowl? I feel like that would help the experiment.
Yeah.
Hmm.
And like just get like a metal cooking bowl and then like try that.
I bet you there's one in the
I might
cafeteria.
get I might get one of those peaches tins. I've been hankering for peaches lately, so I might get a peach tin. All right, I could try that
So
again. I could try that again on Friday. Any other suggestions?
Pour a bunch of gasoline on it before you try
Yes.
again.
What?
Mr.
I
Hendro,
know
can you have
gasoline
like
is cheap right now, but I'm not crazy.
can you buy gloves that will stop you from grounding an object so you can just hold the bowl without grounding it?
Well, the problem is that this is not like a charge that flows. This is static electricity. Static electricity has a few different properties than the charge that you normally have in a mains outlet. So a mains outlet has a whole bunch of electrons moving. So the charge is really, really high. Your Q value is very high. And so your voltage is low. Now, you can get the same amount of work done if you make the voltage really high and the coulombs and amps really low. While if you use an insulator, it will stop flowing electricity, like AC or DC current. you'll stop an electrical current. It doesn't do as much for a an insulator doesn't do as much for static electricity. You can tinker with it because if you use an insulator with static electricity, you have a thing called a dielectric. And this is basically a way that you can use conductors. It's a trick that you can do with conductors and static electricity. So when you use a dielectric, you have this very unusual thing where you can get, do you remember how you induced a current or induced a charge in something? Anyone?
I think, yeah.
Where's my annotations? Okay, I want to annotate the whiteboard. Okay, so if I was to have a particular object, and if I was to have this object, let's just have this as my protons. Okay, I want them roughly spaced out equally. If I have my protons roughly spaced out like this, for every proton there will be an equal and opposite charge in an, what's the opposite charge of a proton?
Negative.
Yeah, so you have a negative charge in a what?
Electron.
Okay, I'm going to get the electrons blue. Come on. So every electron should, that's not going to work. Let's make that shape. That's going to cover it completely. So every one of these should have an electron. Why can't I copy you and make you into an array? Problematic.
Just make it a bunch of blue X's and just set them like right next to it.
I guess. Or I could just make them stars, I guess. And I want to do this up here for a reason. Okay, so let's say you have a substance. That's not good. That's not in a line. When you have these substances with the electrons and the protons, they normally line up. Now, you can't really get the electrons to leave. Like they should kind of line up there. What you can do at most, if you polarize an object, is the charge doesn't necessarily all move to one side. What it does is you get it to shift a bit like that. So this side will act more like electrons, and as in be negatively charged, and this side will be positively charged. And then when you move the charge to the other side, it'll polarize this way. That's what's happening with the electrons that move. The electrons can move around here. They're attached to their protons, and they can't leave, but they can kind of move towards one edge. This is what when you polarize an object that's not a conductor, you can still have a charge there, even though this will never conduct electrical current.
The proton never moves, right?
Chemically, no, not normally. I mean, you've seen what it looks like in, so like, let's say you had not a metal. What's one and a good example? So if you have like your this is polyvinyl chloride, PVC. These pipes are PVC. Now they can still have a static charge, even though all their atoms are in a hydrocarbon chain. They're stuck. They don't move around. The atoms don't move around. So no, the protons don't move. But the electrons will move from one side of the atom to the other side. They'll just generally be more to the other side of the atom, like what you're seeing here. So if I'm going to move this off so I don't lose that. If I put a whopping great big negative charge here, I've already done negative charges as a line, so I'll just stick with positive charge. If I put a whopping great big positive charge here, let's say I put the positive charge there, what's going to happen to the positive charges in the substance? Will they want to be close or further away?
Further away.
Okay. And the negative charges will want to be,
Closer.
so this will happen. They won't break off and do this, but they'll just move slightly, blink, like that. And that leaves this side of the object negatively charged and this side positively charged. That happens because the electrons are not free to leave their atoms. And this is why when you say, can I add an insulator? Yeah, kind of, but not really. This will stop a whole bunch of electrons coming in. So if I had a whole bunch of electrons coming in here in a charge with, say, 240 volts, and they're all coming in gangbusters ready to bully their way into the object, these electrons here will stop that because, I mean, they'll get pushed out of the way a bit, but it'll stop the whole thing from moving because they're tied to their protons. That's what an insulator does. If it was a conductor, a metal, what would happen? I'll take a coffee while you think about that. What happens if this object is a conductor and not an insulator?
Wouldn't it flow through?
The electrons
Yep.
flow
through. So the new electrons coming in would push the old electrons out. And that is your current.
How
Moving
much
through.
to train
So
it?
that's basically a segment of a wire.
Pardon?
So it's basically kind of like that little box is part of a wire.
Yes, exactly right. If it was a conductor.
What
If it-
happens if it's not?
If it's not, what you can do is you can move the electrons around their orbits of the protons, but you can't actually get them to leave. So I can make the top positively charged, I can make the bottom positively charged, I can make the left, I can make the right positively charged, but I cannot get rid of these electrons. Make sense?
Yes, 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 yes.
Okay.
Yes.
So with static electricity, you're not talking about flowing current. You're talking about this sort of movement, and you can still get that charge there. In fact, with static electricity, if you put the voltage up high enough, this thing is really, really, really aching to get off the electrons are aching to get off the protons. In fact, they might even be kind of like stretched all the way that way, because if you're talking about things like P shells, etc., you're going to get really weird shapes. So sometimes if this was, say, the nucleus, the movement of the electrons could be something even like this. And sometimes their shapes are like that. So if you have them only moving in this orbit here and nowhere else, you can get them almost over like an atom over. If that makes sense. And that's where you get the huge amounts of the voltage, the potential difference, because the amount of energy that you're shoving into there is moving the electrons so far away. That's where you get that amount of energy. Whereas the amount of energy you get, you're putting a huge amount of energy in one electron. In flowing current, you're putting a tiny amount of energy in lots of electrons. Same energy, just spread over more charge. Okay?
Okay.
Okay. So to answer your question, no, I'm not going to add an insulator because it doesn't do a huge amount.
I see.
Mr. Hendro, you said you were gonna do the experiment again on Friday. So
I am going to try to do the experiment again on Friday with the suggestions from you guys. Now, the suggestions that were recommended was use a paint tin or a tin that does not have a coating on the inside, because that seems to have wrecked the process. I don't know why. I just want to try using a paint tin, see if that makes a difference.
Do we still need to fill in the the conclusion analysis stuff?
Okay. So, was there a difference when this when this was on the outside of this thing bringing the charge?
Yes, there was a big difference.
There was a huge difference. There was almost no charge coming off this. This was zapping when I was moving the charge onto here from the outside, and I was touching it at the side. I was getting zaps at about 1 or 2 mil. When it was like this, I was getting zaps from about 2 inches.
Oh. Nice.
Okay, so it's just a
So the
limitation
dome
of how much.
spreads it out.
It's a limitation of how much charge you can physically move onto this.
So we're gonna do the experiment Friday again, so we don't need to
No. You can finish your write up now. I basically want to see you say, or I want to see you understand that the inside of an object has no charge, or no electric field, I should say. Because it has no electric field, if you put something with static electric potential difference, or a higher voltage, it will move too, and it will always move too.
I see. Wait, but I thought we were saying, I thought this whole experiment was to say that if you put the charge in the middle, the thing can hold more charge, but if you put it on the outside, it can only hold like a certain amount.
No. Wait. What allows you to hold the charge is the property of the air around it. That's what holds the charge. So if you pass that amount of charge, it will zap. What you're showing is, if I can get this up, let's say I can get this to about, can I do the charge difference? Let's say I'm getting that up to about 1,000, 2,000 volts. Let's say that little knobby bit. Let's say that little knobby bit that we have is 2,000 volts. Okay. If I can get this thing up to 2,000 volts, then if I put an object next to it that's 0 volts, what's going to happen to when they touch?
They'll both have 2,000
Evens
volts.
out.
Yep.
No, they don't both have 2,000
Wait,
volts.
it transfer, right? So one
So
has
one-
2,000.
You will
One
get
has
a
zero.
number between 0 and 2,000 depending on the surface area.
But
So
I
the
thought
number,
you said transfer all.
you don't transfer all, you transfer some, because as you're,
Yeah.
I don't want to do this, I want to make it into a round object. So that
I thought you said if an object with volts transfer to the inside of a surface, then it transfer all of it.
no, or if it's on the inside. I'm talking about the outside at the moment.
Oh, this is the outside right now? Okay.
Yeah,
okay.
the outside you can only transfer some. So if these are both positively charged, your electric fields are going out. Let's say this is the electric field you start with, okay? You start with that electric field. When you do the second, when you touched it already, it'll be that electric field will still be over both. Okay, so you have this object now touched, and then you move it away again. It will be, let's say it's the sum, so you get an equal amount. If I make them completely the same, that's probably a better way to do it. If I make it completely the same, then the numbers will have to be the same on the charges because the surface area will be the same. So let's just make it exactly the same for argument's sake. We're only looking at the outside. Okay, so if I have a field line coming out here, and this one has 0. Afterwards, let's see if I can get dead half there. Okay. Can you see how these two arrows are the sum of that charge?
Yes.
Okay. And they will be equal and opposite in direction okay. That's what you'll get. That's what you'll get after you've touched, correct?
Correct.
I'm so confused.
So now let's say I move this away and recharge it up again. If I recharge it up again, I'm not putting it onto a 0. I'm putting it onto one that's already got a charge. What will happen when I try to make these two charges connect? Will
Then
they're
the
both
arrow-
positive, will they attract or will they repel?
They will repel.
They'll
Repel.
repel. And the difference is much less. Let's say if this difference in electric field strength is 10, at this point it's 10. If the electric field strength here is 10 volts per meter, let's say that's the electric field strength there. If I've already done this before, and this is going in the opposite direction, this is 5 volts per meter. Can I get, don't do that. Can I get this to transfer the same amount?
What do you mean, like same amount? So like 7.5, 7.5?
It'll be 7.5, 7.5. And the next time you do it, it'll be?
In the middle of 17.5.
Yeah, so the middle of 7.5 and? Can you see how can you see how that's going to be a curve? It'll get close to 10, but it will never ever get to 10 volts.
Okay.
You can get it close to 10 volts, but you'll never get it to 10 volts. Compare that to what will happen if you put it on the inside. If you put it on the inside, what will happen is you will get it'll start at 0. And the first one you put in, all the charge will transfer through. Does all the charge transfer through? Yeah, it should all transfer through because the potential difference is always going to be on the inside 0 and whatever here until they get close to being the same. Until they're the same and there's no potential difference, all the electrons will flow out. So you're going to get an increase of 10 volts on the outside. The next time you do it, it'll be 20 volts. The next time you'll do it, it'll be 30 volts. So that rate of increase by putting it on the inside should be faster than on the outside, and there's no limit. The only limit you have by putting the charge on the outside, the only limit you have is the air.
Which I thought was like 6 or 3 million, right? 3
Yes,
million
about 3 million. Once you get
volts
to
per meter.
Once you get 3 million volts per meter, you start to disintegrate the air and turn it into a conductor. Disintegrate the air? Well, you turn the air into a plasma of sorts. Okay? Which leads me to a very interesting question. What are the static bags that you get with your electrical items?
What's a static bag?
You've never seen a static bag.
I don't know what it is. Maybe I've seen it, but I don't know what it is.
Okay. Let's share screen and go to a webby page, and we'll look up a static bag. So these little silvery static bags. Have you ever seen one of them? The bag that's around the item in here.
I think so.
You can see a bag like that.
I think so.
What do you notice about it?
It's transparent.
Bag
Yeah, and what else does it have?
lines.
What do you think those lines might be?
I don't know.
Conductors?
That's a pretty good guess. I would say they're conductors as well. If you have that conductor on the outside, are you going to get the static inside?
No.
No. You're going to have whatever static gets there, it might be charged really, really high, but on the inside, whatever this piece of electronic equipment is, it's going to be statically stable on the inside because there will be no charge. If you have that little electronic board and you put it inside there and it had some static charge, what would happen to that static charge?
Zap.
Attract.
Would it go? Would it stay there? Would it go away? If you have if the inside the wall, if I put the little electronic chip, I'm going to make a green electronic chip. If I put it inside a static bag, and the inside of this static bag is always at 0 volts, and let's say this goes in. Let's say this goes in at, I don't know. Let's say it was connected to the mains or something, and it's got 220 volts worth of static electrical potential difference. So there's a difference in the electrical potential energy on this object on the outside. If it wasn't a closed surface and you were just touching it to something, you might equalize. You might get something like 110 volts on both surfaces, but because all the charge will leave, it'll go to the outside. There will still be 0 on the inside. Let's say that's halved down to 110. It will still leave again. It'll leave again. It'll leave again, because 110 is higher than 0. 220 is higher than 0. It'll just keep going down till, I mean, even if it's got 1 volt higher than the inside of the static electric bag, the static bag, it'll go down to 0. This is how we protect our electronic equipment.
What? How? Wait, because why?
Mr. Hendro, I have no idea what you're saying.
The inside of an object, the inside of a hollow conductive object, always has a electrical potential difference of 0. There is no electric field inside.
Wait, how does this relate to the plastic?
Because if I have a static, static electricity can damage phones and computers and stuff, right?
Yeah.
I don't want it to get damaged. How do I keep the static electricity from affecting my phone?
You put it in
The
the
metal
bag.
phone case.
Or a static bag.
Oh.
Why would you want something that's
Some-
conductive though?
Because it means that the charge will always be on the outside. It's the same.
Ah, but I thought conductive means like it goes through, right?
It goes along.
No.
It doesn't go through, it goes along.
Oh. There's an insulator that goes through.
Here we go. Okay. So I'm going to, stop. Okay, so I'm going to share a video because I want you to see that people can be in a Faraday cage. So this is just chicken wire around a cage, and they have a Tesla coil nearby. Now, a Tesla coil is kind of scary because it
Mr.
not only
Hendro.
has the high voltage, it also has the high current as well. So let's have a
Mr.
look.
Hendro,
Yes, just quickly watch this. That person is standing inside a giant Van de Graaff machine, like big that.
Does
None
he
of the
have to
sides-
hold the bar?
Sorry?
Does he have to hold the bar?
No, he doesn't have to. The problem is if he starts, he can touch the electrical, as long as his hands don't go outside, as long as his hands and feet don't go outside the cage, he's pretty much safe.
Mr.
This is
Hendro,
why in a lightning storm, don't stick your head or arms outside of the car, because your car does the same thing.
Mr. Hendro,
Yeah.
is that like with glass or is that like without glass? That's with glass.
No,
right?
that's chicken wire. Here, it shows it at the beginning what it's made of. So he's
I
stepping
can't-
inside, and
What
it's-
I'm
can you see the
seeing-
chicken wire? Can you see the chicken wire?
Dylan, it's wire.
A little, yeah, okay. I thought it was just like that box. I'm like, well,
No, it's chicken wire. There's chicken wire around it. It's a conductor.
That's
Mr. Hendro,
awesome.
it's time.
Do you have somewhere to be?
It's past time. I have stuff to work
Bed.
on.
You have
I
stuff
have
to work
bed.
on. Okay.
Electives.
Yes, Mr. Hendro.
It's not science.
Okay.
And the
if you-
worst part is I didn't get anything, so oof. Please upload and
I will upload this. If you
Yes.
can write up your experiment from this piece of information, you may. I'm quite happy with that.
That's
Okay.
Mr. Hendro.
Wait till Friday.
Pardon?
Can we wait till Friday for the conclusion?
Sure. I don't mind about that. Has anybody tried to do the test yet?
No, I thought we were supposed to wait for the
No.
test, for the experiments to be done.
we can't
We
access it.
can't access it. I already told you.
What?
It says
It
you
said
need
request for access.
permission.
You gotta check your Google Class comments, please.
Why don't we all go to the same thing? All right. Okay. Thank you, ladies and gentlemen. I won't keep you from your
Thank
next
you,
class.
Mr. Andrew.
Thank you, Mr.
Thank you, Mr.
Hendro.
Hendro.
Thank you,
Thank
Mr.
you.
Hendro.
Thank you, Mr. Andrew. Yeah.
Thank you, Mr. Hendro.
Oh wait, Mr. Hendro, by the way, the conductor lets the electron stay out.
The what?
The conductor, you said like the conductors let something stay out.
The
of
conductor
hollow
lets
thing.
something stay out.
Yeah, he said something like that. Or never mind.
I don't know what that means.
Never mind. Thank you, Mr. Hendro.
Okay.